We recorded several videos of flow visualization. The first video is the one we used to calculate one value of the Struhl number at a known airspeed. To calculate the Struhl number, one needs to know the frequency of vortex shedding, F, the characteristic length, L, in our case the cylinder diameter, and the flow velocity, U. In order to find the frequency of vortex shedding, I slow the video down to just 1 frame at a time, which in this case is actually less than 1 frame per second. I looked for patterns in the flow. You can see how the flow moves over the top of the cylinder, highlighted in green by the laser shining down on the smoke in the tunnel. Then the flow gets sucked down the backside of the cylinder. It's hard to see at this point as the smoke gets pulled further and further apart, but the remaining smoke dissipates in the last frame, further behind the cylinder. This cycle then repeats and does so several times per second. By manually counting each second, frame by frame, we can track this process. I counted several times and checked with other members of my group. As far as we've been able to discern, this process occurs 11 times per second, approximately. So F is 1 over 11 seconds, or 0.90909 1 over seconds. The length, or in this case the diameter of the cylinder, was 6.25 inches, or 0.15875 meters. The turbine spun at 150 revolutions per minute in this video, and that comes to about 5.85 meters per second airspeed. This gives a Struhl number of 0.024667 or 975, or about 0.025. Given that you calculate the Struhl number by the frequency times the characteristic length divided by the airspeed. But what exactly does this number mean? According to Wikipedia, the Struhl number describes oscillating flow mechanisms. On an order of about 10 to minus 4 and below, this means that the flow is high speed and is almost steady state, but at about order of 1, the viscosity dominates flow, resulting in collective oscillating movements. As you can sort of tell, 0.025 is somewhere in between these two. I also found a graph on Wikipedia describing a similar test to the one we conducted in the graph. The graph appears to indicate that our Struhl number should be on the order of magnitude of about 10 times greater than that of what it is. The Wikipedia graph isn't entirely specific as to what characteristic length their test cylinder used, but does provide Reynolds number information. As such, while this graph was useful for determining what value the Struhl number has and what it means, I'm not sure we should compare our number to it. One thing that is also worth mentioning is that when we turned the laser perpendicular to the flow of smoke, we found intense vortices in the air prior to the smoke encountering the cylinder. Our best theory for what's causing this is that the smoke leaves the smoke machine already with those vortices and doesn't get quite straightened out by the inlet grate at the front of the tunnel. This could have had some effect on our results. Another thing that's also worth mentioning is that we could have looked at multiple different videos to find the Struhl number at different velocities, at different airspeeds. The problem was this video was the clearest representation of these vortices that we were able to track, this vortex shedding, and it was the only one that we were able to really make out where the vortexes were happening and at the frequency that they were shedding. So it was really the only one that we could use to calculate the Struhl number, and that's why we chose this video and went through this process.